Hey everyone, welcome back to part 3 of the MCQ series. In this video, we are going to cover some of the very important concepts, particularly collection framework, map, hash map, and a lot important about what function does what work, and also we look into DP and some probable topics over there. So let's get started. The first we have over here is map. What is map? It's an interface. It offers some key value pair based data structures. So what map offers us, it basically is implemented using a hash table. Okay. And why we use hash table? So that we can achieve constant time operations for insertion, deletion, or lookup. Okay. Now we have three types of map. So hash map, tree map, linked hash maps. These are basically classes which implements the map interface. The thing that we have to focus over here is the difference. So you can give a glance at this. I'll first let you go with some important points over here, and then you can read the complete table. The first point over here is ordering, and the most important is that tree map has sorted by keys order. Hash map has some random order, no guaranteed order, and linked hash map, as the name suggests, as you insert or the way you insert is the same that is retrieved over there. So it maintains the access order. The next, null keys. Only one null key is allowed for hash map or linked hash map, but not allowed for tree map, as you can see over here. So this is a very important point. Again, the null values are allowed for everyone. Synchronization, not synchronized. And for tree map, it's login time complexity for insertion, deletion, or lookups. For the rest, two, it's big of one. And then the most important is the underlying data structure. So for tree map, you can see we have red black trees. For hash map, we have hash tables. And for linked hash map, we have a combination of hash table plus doubly linked list, not single linked list, not over there. That's the use cases. So based on the differences, some normal questions could be asked. Next is if you have to convert hash map to tree map. So what are the approaches that you can follow? Basically four approaches. You must remember that collectors, vanilla, guava, and manual conversion. Okay, and this is a very important statement over here. That is, we can create a tree map object, and inside the constructor part, we can send the hash map, and this will convert the hash map into tree map in a very simple approach. Okay, moving ahead, we have sets. Now, set is again an interface or collection framework that does not allow duplicate elements. Okay, similar like HashMap, it also offers some classes that implements the set interface. So same over there is over here also. We have hash set as hash map, linked hash set as hash map, and tree set as tree map. Okay, everything is same. The points discussed over there is same for here also. You may give a glance. Everything is same over there. Okay, so if you remember one of the two tables, you will be able to solve the questions related to the differences. Okay. Moving ahead, we have a program topic name distributing items when a person cannot take more than two items of the same type. You might already know the problem statement, and that is we have k people, we have to distribute some items, and we have to make sure that there is no item that is greater than two times k, that is number of people. If that is the case, then it's an invalid scenario, and we cannot distribute items such that everyone gets equal to two items. So what we do is we read the input people k, total items n, then the array n of items. Then what we do a frequency calculation of the items. And then at that time, frequency calculation, we see if there is an element whose frequency is more than 2k, then we say it's an invalid case. The observations are very important. That is, if an example input is given and they say that check if it's a valid case or not for MCQ point of view. So it could be like the array is given which is empty. So for items empty array is always a valid scenario. And this is a very trick question where I'm sure many would use to say that it's an invalid case. If it's empty, we don't have to check, okay, but it's a valid case. Because make sure the word is it should be less than or equal to 2k. Okay. Next is if items are same, then if an item is same, and if the count is more than 2k, then it's an invalid case. Next is an item that can appear to be saved is maximum to be 2k, equal to 2. If it's more than 2k, then it's an invalid case. So the question is, how much at max can an item be? Answer is 2k. Okay. Coming to time and space, so it's big of n because we are traveling on the array, calculating the frequencies, okay? And because we're using the hash map, so the number of unique item key value pairs is the space complexity for the hash map. So we have big of m over here, where m are some unique items. Okay. Before moving ahead to dynamic programming, we must first dive into a very important concept over here. That is, I'll just now what we have to do, we have to check hash map functions, and it's very important. So what we can do, we can go to the Oracle website and give a glance at the functions which are offered by map interface. Okay, so just scroll down more. Uh, that's it. So a lot of functions are over here. We'll first go to some important functions and then you can yourself go to this website and read once because there could be a scenario in general based on collections, be it linked list, hash map, sets, or array list even. So they might ask that what this function does. So if you don't know about the function use case, you might pick a wrong answer, right? Moving ahead. So let's swipe up. Is empty. I'm sure most of you know that it returns a true false and checks if it's empty or not. Okay, key set will get the keys and values. Small v will get the values. Okay, it's over here. So this returns values. That returns key set. Okay, now put for adding, put all for adding most of the things. Okay, put if absent for frequency calculation, obvious reasons. Replaces there. This is the scenario. We have two replaces. So replaces the entry for the specified key only if currently mapped to some value, and this one if only currently mapped, if only. So replaces this. And what else could be asked? Contains key. I'm sure you must know that it check the key exists or not and returns a true false. So you must know what is the return type, what the method does. Okay, clear will remove the map and clean it. Okay, clone is for copying the map. Shallow copy is the keyword over here. Okay, so these were some important. Let's see for linked list. Oracle. Okay, so we'll go to this side, swipe down. Nice. So we have an add method. Okay, just it returns a boolean data type and it appends the values, the specified elements, to the end of the linked list. This is very important end. Next we have add. So we have index comma elements. So at some index that element will be added. Add all will add a lot of elements. Again, add all. For this we'll have a lot of elements added for a particular index. Add first, add last, as the name suggests, would add at the first, beginning side, ending side, clear, clone. Okay, contains, we'll check if that is there in the linked list. We have get for index, get first, get last, index of, will get on the index of first occurrence. Remember the first occurrence. And last index of will get the last occurrence. Okay, of a specified object. Next we have offer. What offer does? Adds the specified element, tail size, last element of the list. So from the end size of a first, of a last, same like add first, add last. Okay. Next, what we have is that peak. Now you might confuse from peak over here because it's basically used for stack, right? There in stack, we say peak function is the top value. So what does peak does over here? Is this retrieving the top value? That is, let's say top is the beginning part. Let's see. So retrieves but does not remove, same as stack, and that is the head. So remember, whenever we are talking about linked list, the head side is considered as the beginning and the tail side is considered as ending. Okay. Now peak is clear, it will check for the head side and it will tell what is the value for head. Okay. Peak first, peak last, same like looking from the first beginning side, head side, looking from the tail side, that is the last. Okay. Pole, what does pole do again? Now removes the head. So you might consider a very important point that whenever some peak point is there, whenever some removing is there, something like that. So we are first focused about heading. That is the beginning. Remember the beginning. Next is pole first, post last, same as remove first and last. Next we have pop. What pop does? Elements from the stack represented by the list. So again, it will get out from the beginning. Push pushes an element onto the stack represented by the list. Again, pushes an element in the beginning side. Okay. So I like to share that this was the thing that I got wrong for my exam. So make sure you remember what this function does actually. The point to note over here is most of the functions focus on the beginning side, that is the head side. Okay. So if such question is asked, For linked list, you may take the beginning or the head as the answer to that question. Remove Remove by default removes the head. Again, you may see from the beginning part. Remove index, remove at the particular index. Remove first occurrence. Same like index of. Remove last. Returns the last element from the list for that particular returning. And then remove last occurrence like index, last index of. Okay, like set to add some element at particular index, size. Of. So these were the some important, and the points to notice over here is peak, hole, pop, push, because these are common for stack and queue basically. And asking these for linked list point of view would obviously confuse anyone. Okay, moving ahead, let's see for hash set as well. We'll go to Oracle's website, docs, and spike down. So these also have some obvious methods, and you may see for hash set we don't have much methods. Very limited amount is there. So add will add element to the set if not already present. Okay, because it considers that duplicate should not be included. Clear will remove everything. Clone will make a shallow copy. Contains will check if it's there or not. Is empty will check if it's empty or not. Iterator is a upper class that is shareable by all the collections framework. Note all the collection framework. So it's iterable or iterator, you may see that. But this could be also asked, and this will help you to traverse on the hash set, hash map, or any collection framework. Okay. Next is remove. So remove the specified element, size and split iterator creates a layered binding. This won't be asked probably because it's some advanced use case. Okay. Coming ahead, we have hash map is done, hash set is done, list is done. Next we have stack, we have queue, we have deck, and these are pretty easy to answer because the methods used over here are self-explanatory. You can again go and search for stack oracle. Okay, and then you can read this to the glance. I'll let you know in a brief point. So again, a very limited amount is there. Search is there, we search and returns one based indexing position, like a point, one based. Not like if the element is there zeroth index. No, it will say for zeroth index one. For first index will say two. Okay. Similarly, push for element, pop is there, peak is there, and peak. Okay, let's quickly see for oracle. Okay. So these are the functions very similar to stack, add element, offer, poll, peak, remove. Okay. So we don't have a push over here, don't have a pop over here, but we have a peak that is common. So we use offer for adding, poll for removing. That is the thing. Okay. Is there anything important? Again, we can also give a glance to add a list. So, okay. So we have a bunch of methods over here, and you can give a glance. It's similar to the previous we have seen. Okay. Not much difficult. But yes, when linked list is there, hash map is there, hash set is there, those are very important data structures that are probable to be asked from methods point of view. Okay. So do give a glance at these three and read once. Just read once and read properly. Okay. Moving ahead to dynamic programming. So yes. So what we have is that the first point over here is that we must know when to apply dynamic programming. This is again an MCQ question. So if an overlapping subproblem is there, then we will apply dynamic programming. If optimal substructure is there, then we will apply dynamic programming. When there is a need to store the answers of subproblem, then we will apply dynamic programming. Whenever a recursive code dives into a polynomial time complexity of say n power 3, that is 2 power n or something like that, then is the need for dynamic programming. When greedy approach fails, then is the need for dynamic programming. Or when there is a risk of stack overflow due to too many recursive calls, then there is a need for dynamic programming. Okay. So these are some features, some qualities that let us force, that enforce us to use the concept of dynamic programming. And it's a very good technique. What is just basically the theoretical definition? That's an algorithmic technique solve complex problems by breaking into simpler subproblems, storing them into some data structure so that when we are coming back to solve the same repeated subproblem, that is the overlapping subproblem, so there's no need to recalculate redundant calculations to reduce them. That's the main concept over here. Okay, moving ahead, we have two types over here. One is top-down, what I say as TD, bottom-up, that is BU. Other name is top-down has memoization, bottom-up has the name as tabulation. As the name suggests, memoization means we are remembering something. Okay, memorizing. What we do is that we have the same recursive approach, and in that we have an edit, that is, we send a DP, maybe a 1D DP, 2D DP, that is the array, as a parameter in the function signature. And whenever we are going to calculate, after the base case, we'll put an if condition. If that is already stored in the array, then don't recalculate, just return that so that the sub problem won't be recalculated next time. So that is what we do. We can use 1D, 2D to remember. Okay. And from time complexity point of view, it reduces because we are not calculating the overlapping sub problem. But the space complexity is increased because initially due to recursion we had stack calls. Now we also have a DP array from space complexity. Coming to next approach is tabulation, bottom up, BU. And what we do over here is that it's an iterative approach. Now we got rid of the space complexities improved because we got the stack call space. Because we no longer have the recursion concept used over here, we are doing iterative approach. We have an array 1D, 2D, DP, and through for loops, while loops or so, we are filling up. And in a way, we find an answer at a particular cell. So this is an enhanced approach, right? So I hope that's very clear. So what we do is that first step is to write the recursive approach. Then the recursive approach fails because of time limit exceed error, TLE. Then we have to improve that through memoization. The next step is because memoization has stack calls plus array space. So we have to improve the space complexity. So we come up to tabulation where the stack call is not existing. And the last step, which most of the people neglect, is the space optimization. That is, whenever DP is used 1D, 2D DP, we can even reduce that to big of 1 or big of n for 2D DP as well. That's the most neglected part, and it's not very important from MCQ point of view, but yes, from code point of view, you could give a glance at that. Okay, moving ahead, we have some problem. So you must know the names for these, at least those which are not stricken off, and even those who have been stricken off, because could be a scenario we asked in MCQ that which of the following is not a DP problem, and then you must know what are actually solving using a DP problem. So these are some famous problems. Okay, and those which I have stricken off could also be same ones remembered from my. There's very less probability, but yes, a very basic, straightforward question that check which one is used, which one uses the dynamic programming approach, which does not use, and so. Okay. So in total, we have 1, 2, 3, 4, 5, 6, 7. If we neglect the basic problem, so we have total 6 problems over here from code point of view in syllabus or so. Okay. Moving ahead, what could be asked over here is that you must know the time and space boundary for sure. That's a very simple question. Next year, you should know the recurrence relations. You must know the base cases. You must know what DP you're using, 1D or 2D. At what particular cell is the answer coming up? Okay. Next, what are the formulas that you're using in the recurrence relations? So that's all could be asked. And the next is that maybe they were numerical input and they ask you to apply the concept of, say, least common subsequence, longest common subsequence, longest palindromic subsequence, or so on, then pick the answer. So you must know from code point of view also the statements, the lines used over there. And you must also practice a numerical to solve and then pick the answer. That is an application to this algorithm, right? So moving ahead, Fibonacci is a very basic problem where the next term is the sum of previous two elements. Okay. The base case is that the first and the second, that is the zeroth element of the first term, is already predefined. And this is the reconciliation that we'll be using. What we do is that we create a DP of n plus 1 size because we'll get the answer as nth index, and we filled it using this expression, and at the end we return the DP at n, that is the nth index element. And this would also be reduced because over here the space complexity is n because of the DP array. But in case we take only two variables, that is previous, previous to, and so, because we have included, we only need the values of the two previous elements. We don't need to store them again and again. So yes, the space complexity could be reduced to big of 1. And this is a little bit of controversial question because if say the question is asked like what is the space complexity for tabulation approach? Okay, so you will say like according to this table is big of n, right? But what if I say that big of 1 could be also a probable answer? And what if I say both are there in the MCQ? Then what would you do? So make sure you follow the table and tick accordingly. You might not know what is the answer ticked by them. According to me, the most probable answer could be big of 1 because tabulation basically means for loop, not basically the DP filling. Okay. And if I'm putting a for loop, but I'm not including a DP, I'm using some variables to reduce the space complexity. So that is the best answer to tick if the space complexity is asked. So I would say big of 1 for tabulation. You might say big of 1. Okay, do let me know in the comment section what do you think. Okay, and for obvious reasons, the questions for DP most of the time has 2 power n, 2 power n plus 1. So time complexity is for recursion. Okay, and whenever recursion is there, we have stack calls as space complexity. So you can give a glance at this table. Moving ahead, we have longest common subsequence where two strings are given, and we have to find what is the common subsequence. Note that subsequence and substrings are two different things. They are not equal. What is subsequent? What is substring? This could be also asked as a normal MCQ question. So that is every subset, every substring is a subsequence, but not vice versa. And in subsequence order matters. That is, if an element is there, if two characters are there, one character is before another character, that should be maintained in the answer string also. Okay. So again, the base case reconciliations, that is if character matches. So what we do 1 plus TP of diagonal upwards, I minus 1, J minus 1, or otherwise we do max of left cell, right top cell, something like that. Okay. So this is the code. You have the basic access conditions over here. And you must know this because this is the formula that will be asked. So, okay. We have a DP of mn, n plus 1, n plus 1 size, and we got the answer as DP of mn. That is for the array, nth index, nth index, that is nth row, nth column. Okay. And this is the basic snippet. If we are asked to print what is the string, okay, you can give a glance to that also. Good, good to go. And supposedly, this is the question asked, that is, can LCS be extended to more than two sequences? So the program or the algorithm that you will be using is basically the simplest one using for two string, that is say string 1, string 2. Okay, str1, str. But make sure this could also be increased for string 3, string 4, and so. What changes will happen, that is 2D DP will change to multi-dimensional DP, multi-dimensional array. Okay, say 3D arrays, 4D arrays. So the recognition will remain the same more or less, but you have to make some edits over it. Okay. Now, when I saw this word contiguous, I remembered another question over there, that is arrays are a contiguous memory data structure. Okay. And linked lists are continuous. Remember, arrays are contiguous, linked lists are continuous or non-contiguous. Okay. This could be also asked. A trick question which most of us are not aware of. Okay. Coming to time and space, so memorization tabulation have time of n cross m and n cross m because of the space complexity used for deep gathering. And then this could be reduced, space could be reduced to m or n, something like that. Okay. And the question will again have 2 power something, and over here we have 2 power n plus m. Going ahead, we have longest increasing subsequence. What's the problem statement is that they will be given an array as the name subsequence suggests. The order doesn't matter, but it's not like continuous order doesn't matter. It's like the relative ordering matters. Okay. And we should have an increasing subsequence that should be coming from the original array. Okay. Now, again, two scenarios could be out from program point of view. That is, what is the length of the longest increasing subsequence, and what is the actual elements in that length. The formula point of view could be asked. Okay, so it's like we have this for loop for base is for previous, and if current one is less than previous plus one, so we do current equal to previous plus one, something like that. So, and in the array, that is 1D DP values in the 1D array. So we fill the array and then we find what's the maximum element, and that's the length of the longest increasing subsequence. Okay, and other thing is that an optimized solution using Bayesian sorting could be used, or binary search approach, where the time complexity could be n log n. Okay, so note this is a trick question could be asked, and again the recurrence will have 2 power n. For tabulation memorization, we could have n square, and space optimization we could n. Next is LPS, longest palindromic. It's an application to LCS. Even LIS is an application of LCS. And what we have to find is palindromic subsequence. Palindromic means what reads same from left to right and right to left. Over here again, an example input could be given. Could be asked what is an invalid answer that is not a valid palindromic subsequence. You could be asked to solve and then pick it. And even the recurrence solution could be asked. So these formulas could be asked. That is I plus 1 j minus 1 plus 2 we do if condition and else condition we do I plus 1 j I j minus 1. That's what for these cases. Okay, so coming forward, this is the DP tabulation, and these were the formulas that we could remember because it will be asked. DP that we are using is n cross n DP, and the answer, final answer is that DP at 0 and n minus 1. Okay, and if you do from LCS application point of view, so the answer will be at DP of nn. Okay, so this is the chart for space-time. Moving ahead, we have subset sum problem. It's an application, a variation of 0-1 knapsack, where we are not concerned about the maximum value, or we don't need to check the existence of a subset that matches the sum. But we have to say true or false or yes or no if there exists a subset whose sum is exactly equal to target. Okay, coming ahead, the take not take approach we use because of subsequence obvious reasons. And remember the formulas we are using over here. That is, if 2D DP we are using, okay, so it's like I minus 1 j, I minus 1 j minus error, I minus 1, and we are using the OR operator over here to sticks, as you can see, and this is the current pick when we are not making any change. So you must remember the expressions. Okay, again, this is the chart n cross target. Now, LCS, LIS, and LPS have share a similar time and space memory chart, and 0-1 knapsack and subsequent share a similar. Okay, target will have O of target will be for space optimized. Moving ahead, we have 0-1 knapsack where some values and dates will be given. Knapsack is basically a bag where we have to put items to get maximum value, maximum profit, but we should not exceed the capacity of the bag. Okay? And over here, 0-1 means that we will either include or we will not. So if an element whose weight is more than the remaining capacity of the bag, in that case, we ignore it and move to the next element, next item. Okay? So you must remember the formulas. The recursive approach is shared over here. And for tabulation, this is the formula. Okay, for this condition, else condition, if condition, break case. Okay. Going ahead, we cross use a 2TDP. So in case you use a n and w plus 1 dp, so you will get an answer at n minus 1 w. In case you use n plus 1 w plus 1, so you will get an answer at n and w. Okay. And we have next similar to this is fractional knapsack, which uses value by gate ratio concept and space comes here and log n. Could be asked, like, what is that? And this is the chart you can see once. Okay. Coming to the last topic before the end is the rod cutting problem. It's not similar to any of the previous groups. It's the third variety, and it's based on unbounded 0, 1 knapsack problem. Okay. So the question is, we'll be given a prices array, and each price is bigger index. That is, we are cutting a rod at length 1, length 2, length 3, length 4. So at max we have to cut. We have to cut in a way that we get total length as 4, and we get maximum profit. In this case, what I'll do, I'll make 2 cuts for 2 lengths so that we get answer as 10. Okay, you can see this is the dry run. Again, we have two approaches discussed over here, the recursive, the tabulation approach. Okay, you must remember this formula. Okay, coming ahead, next we have used a DP of 1D DP and plus 1 size, we get answer at n. Now over here, we can also use a matrix exponential technique where we get a time value of n log n. Okay, variation of unbounded knapsack, and this is the time space chart. You can give a glance at that. Okay, so they have some practice questions. Give a read to it. So this Excel sheet is very helpful for time-space complexity analysis. It has some errors which I'll resolve and then share that with the version. This could be also very useful. Okay. Coming to the topics at a glance, what we can have. So let's summarize. For loop detection, when is the loop detected? That is when the slow and fast motor reaches at same position. Okay. Next we use Ployson quantum. Sort the bytonic PLL. What's meaning of bytonic? What approach we use is merge sort. Segregate even odd. Space compulsory of because one because we use pointers over there. Okay. Doubly linked list, no, singly linked list concept is given as merge sort. We are merging and then sorting based on conquer and divide approach. Divide and conquer approach. Means type problem. Celebrity problem. So who is called a celebrity? Who knows nobody, but everyone knows him. Okay. And it's an application of stack data structure. Tower of Women. If n discarded, then total how many moves we have to take? That is 2 per n minus 10. So if 7 discarded, 2 per 7, 120 minus 1, 127 will be answer. Stock span problem. If an input array is given, they will ask what is the stock span for the array. That is given prices of the stocks, and we have to find the stock span. Priority. Again, this uses inter-review, minimum heat, maximum heat concept. Sorted extra space, as the name says, without extra space, the space number should be 1, and we would use a sort of selection sort, insertion sort, bubble sort, those in place sorting techniques. Okay, so n square dimensities, maximum sliding windows, stack competition. The question could be like an input array be given, and we would ask tick which is the invalid array. The invalid combination, stack competition could not be reached for that particular option. Okay, recovering the base state. So for optimizing space, constant space, we use Morris approach. Okay, and we have big of n space complexity because we are storing the values. Okay, and over here we use pointers approach also. Okay, next we have views. So this could be like for left view, right view, top view. They would ask what is the particular index for left view, 0 index. For right view, psi minus 1. But if we say from right to left, then 0 index. Top view, first technique of data element, that is Key is horizontal distance from a value. Then in bottom view, last step. In top view, we are seeing from top end, bottom view from bottom to downwards. Okay. We have horizontal view, that is level order tracks, so vertical order tracks, and so next we have boundary traversal. So it will be an anti-clockwise traversal that will take us to the left boundary, then left to right of these, and then right to top, the right boundary, the rightmost end. Okay. Then we have BFS, GFS, purpose search where we use Q for BFS and stack for DFS. Tiles algorithm is used when the waves are small. Bellman code is used when we have negative edges, negative cycles. But the topological sort is there. We use Khan's algorithm. We also use DFS approach. Heap sort is there. This uses by default min heap. Okay. We could also use max heap also based on what we want, ascending order, descending order. Binomial heap, carry heap. Supposing it is a ternary heap is there, so how many children it has? It has three children. Winner tree is there. Then we have the theoretical topics, okay, and the rest is the DP concept. Okay, so that's all. I'll edit it and share this. I hope that's helpful. All the best. Thank you.